Okay, our next talk is by Nikita Nekrasov, who will talk about solution of n equals 2 gauge theory by Cavendish.
Can you hear me? Okay. So I'm going to, this is going to be another kind of matrix model talk. It also could be placed in between the microcosmos and macrocosmos in the Kepler classification of sciences. So I'm not really good at this, sorry. So I'm going to study the UN gauge theory in 4 dimensions with n equals 2 supersymmetry. This is just a reminder. We have the field content of the theory consists of a simple vector multiplet of n equals 2 supersymmetry with a gauge field, 2 fermions, and a complex scalar only in the adjoint representation of the gauge group. And there is a global symmetry of the theory which consists of the Lorentz symmetry SU2 left cross SU2 right, and there are symmetry SU2 internal which rotates these 2 fermions into each other. And also the supersymmetries, there are 2 doublets of this internal symmetry group, the left and the right supercharges. So it is sometimes convenient to formulate a theory in the so-called twisted notations, just that these are the notations which keep only half of the, only 2/3 of the global symmetry manifest, namely I keep the SU2 left of the Lorentz group and the diagonal subgroup of SU2 right and SU2 R symmetry group. So if I rewrite things in terms of these 2 groups, viewing this as a Lorentz group, then I will get different notations for my fermions. So there will be 1 form, subdual 2 form, and a scalar, and also and similarly the superspace fermionic coordinates. And so the supercharges will also acquire different names. So there will be a scalar supercharged Q, a self-dual 2 form, and the vector. And the n equals 2 superalgebra could be written in this form. Now, these notations make simpler the action. So you can write the action in this of the theory as a sum of a topological term, essentially the Instanton charge density, and something which is obtained by acting by the scalar supercharged Q on certain gauge invariant quantity. And the action depends on the Baer coupling, which is a combination of the Baer coupling constant E0 square and the theta angle. And it's convenient to combine them in this complex combination, tau naught. Now, our goal is to determine the low energy effective action of this theory. And the low energy theory will not be the theory of non-abelian vector multiplet, but rather it will be a theory of n-1 U1 vector multiplets. And this low energy action is governed by a single function, the so-called prepotential. So it's a holomorphic function of the scalars in this vector multiplets of U1 to the n-1 gauge symmetry. And it depends on the dynamically generated scale lambda, which depends on the Baer coupling constant in this way. And this m is some ultraviolet mass which we use to regularize the theory at small distances. So our goal is to determine this function f. And if you do perturbation theory, then there is essentially only 1 loop contribution to this function, which you can easily calculate by integrating out the massive W bosons. And then there is a whole series of the non-perturbative Instanton corrections, and this is what we want to determine here. Now, let me just describe the idea of the calculation. It is useful to introduce a symplectic form on my spacetime R4, which I take to be Euclidean spacetime. So just think of the R4 as of some kind of phase space with coordinates x1 and x3 and momenta x2 and x4. And I could also introduce a complex structure on R4 such that this symplectic form will become a Kähler form, dz1 bar plus dz2 bar. Now the choice of this form omega of the symplectic form will break some part of the gauge of the Lorentz group of the group of rotations. So it will be the group U2 which preserves this symplectic form. And for me, it will be necessary to look at the maximal torus of this U2. So it's just the rotations of R4 in two orthogonal planes, the rotations which take x1 into x2 and x3 into x4. And these rotations are generated by a Hamiltonian, which is just a linear combination of z1 modulo squared and z2 modulo squared. So it's Hamiltonian in the sense that if I view my four-dimensional space-time as a phase space and write down the Hamilton equations from this function, then I will just get rotations in these planes which I described. Now, the idea of the calculation is to consider the correlation function, the expectation value of the following observable, which is constructed using the symplectic form omega and this Hamiltonian h. So it's essentially h times the instanton charge density plus certain fermion bilinear and an operator which is the adjoint scalar times the gauge field curvature. So this operator is nice because it is annihilated by a certain combination of the supercharges. So this, for people who are familiar with Donaldson theory, this operator must be familiar because it is annihilated by this scalar supercharge Q. However, it turns out to be to give more mileage to consider this operator together with this term, and that is annihilated by another combination of supercharges. So it's a combination of Q and G. And the nice thing about this H term here is that as H is quadratic in space-time coordinates, under the path integral, the configurations where the instanton charge is distributed in such a way that the instantons are sort of far away from each other are suppressed. And that's cures the problem of so it cures one of the problem of the non-compactness, one of the problems of non-compactness of the instanton moduli space, which has to do with the possibility for instantons to run away from each other. Now, so this function z, so this expectation value in a vacuum where the adjoint Higgs has an expectation value, well, a, can be expanded as a sum over these instanton sectors. So because of these fermion bilinears, the contribution of a given instanton sector with instanton charge k will have something like k times n insertions of this fermion bilinear term and times the exponential of this thing. Now, so this argument can be used to show that the value of the contribution of the given instanton charge is simply the integral over the instanton moduli space of this form. So it's a simplex, so it's some two-form omega, which I will describe on the next slide, times e to the sum function. So the measure on the instanton moduli space, which you get by reducing this observable onto instanton configurations, is essentially defined using a symplectic form, which is this time defined on the moduli space of instantons. So you define it by taking the form on R4 and multiplying it by two variations of the gauge field. So that defines the two form on the space of all gauge fields, which you can then reduce to the instanton moduli space. And then this bolt H, so it's here, it's a linear combination of various Hamiltonians which generate the action of the following symmetry groups on the instanton moduli space. So there is first of all this T2 of rotations of spacetime. So I wrote here how it acts on the gauge field. So it essentially just rotates the coordinates of this on spacetime and multiplies the component of the gauge field according to its as it should transform as a vector field. And then there is also an action of the maximal torus of the gauge group, which rotates the gauge orientation of the instanton And if you just write the gauge field as a matrix, then that's how it will transform. So the point is that we have an instanton moduli space, which we can also view as some kind of phase space. And we have two natural symmetry groups which act on this space. And so this expectation value of that observable is just an integral over this phase space of the exponential of the Hamiltonian of a certain group action. And that is exactly the context in which one can apply the so-called Westermarck-Heckman formula, which reduces the calculation of that type of integrals to accounting of the fixed points of the group action. So the group in question is this torus. You want the n cross T2. And what this formula tells you is that you have to look at all fixed points of this torus action. And at each fixed point, you simply evaluate the weights of the action of this torus on the tangent space at a fixed point, put it in the denominator, multiplied by the exponential of the value of the Hamiltonian at this point, and sum of all fixed points. So instead of taking this complicated integral over this modular space, which we don't really know how it looks like, we only have to enumerate these fixed points and calculate some local data around the fixed point. So the life would be nice and simple. However, this formula assumes that the space over which we take the integral is smooth, essentially, and the fixed points are isolated, and there are no fixed points which are sort of sitting at infinity. So this is not strictly speaking true for the instanton moduli space. So there are several subtleties there, namely that first of all, the fixed points of the action of the gauge group are the point-like instantons, which are not really the gauge field configuration. So they don't belong to the instanton moduli space. If you add them by hands, you get the so-called Uhlenbeck compactification of the instanton moduli space. In that case, you get a singular space, and you still will not be able to apply the Westermarck-Heckman formula. However, one can resolve the singularity of this compactification by going to the space of the so-called non-commutative instantons. I will not describe what it is. I will just state that there is a nice compactification of the modular space of instantons on which these tori, the gauge group torus and the torus of rotations, act in a nice way with isolated fixed points. And and on that space, one can count these fixed points and do this this evaluation as we instructed by Westermarck and Heckman. And it turns out that this counting can be summarized by a single counter integral, which which originally was obtained before this relation to the Westermarck-Heckman formula was understood, by simply looking at the instanton measure. So you get the measure from the you just substitute the instanton field configuration into the original gauge theory action, and you get some measure on the instanton moduli, and then you could play with this measure by adding the q exact terms, where you have to use this combination of the q and g supercharges, and then you will simplify the integral considerably, and you end up with this following counter integral. So it's an integral over the k-dimensional space of phi's, so you have k parameters, and this measure is just so it's some polynomial, some rational function, and so it's a counter integral. So there are no poles, just the counter goes in between the poles of this expression in an appropriate way, and so you get some number of residues, and these residues are labeled by the Young tableaus. So let me try to yeah. So that's an example of the contribution to this counter integral. So that's that's a SU4 gauge theory and instanton charge 22, just as an example. So the contributions to this correlation function are labeled by the 4 tuples of Young diagrams. So it's 4 as in SU4. And for each, so you take the instanton charge, which is 22 here, and partition it as a sum of 4 smaller charges. So it's 12, 5, 1, and 4 here. And then for each partition, you consider the subsequent partition of the small charge. And these small partitions are labeled by the Young tableaus in the usual way. And so these partitions of Young tableaus, they label the fixed points of the Storer action on the instanton moduli space at the same time the residue of this counter integral. And they can also be interpreted in a rather natural way if we use the D-brane realization of this n equals 2 gauge theory. So one way of engineering the theory in question is by looking at the D3 branes sitting at the singularity R4 mod Z2. So if I take fractional D3 branes, and I will need 4 of them to generate SU4 theory. And then in addition, I can add D-1 instantons. And then I will have various configurations when these instantons are stuck to these branes. And in addition, the requirement that these instantons are fixed by the group of rotations will actually pin them to the origin, at the origin of the 4-dimensional spacetime. And there are various ways of arranging these instantons in such a way that they are fixed by the group of rotations. This is not very obvious geometrically, because if this were the ordinary point-like instantons, then the fact that they are fixed by the group of rotations would mean that they sit on top of each other. And so you would not see this finer structure labeled by the Young diagrams, Young tableaus. The point is that we're secretly doing these non-commutative instantons, and they have a structure. So they cannot quite sit on top of each other because of non-commutativity. And so they try to get as close to each other as possible. So essentially, the uncertainty principle lets them. And so you get this, that's how you get these diagrams. Now, if we fix this diagram, then we can actually calculate the contribution of this fixed point to the correlation function, and it's given by a remarkably simple formula. So in fact, it's a ratio. It's a square of the ratio of the determinants of 2 matrices, which consist of. So these matrices depend on the vacuum expectation value of the adjoint Higgs field, and some integers. And these integers are exactly the lengths of the columns of the Young tableaus. And so you get okay. In this way, you get some formula, and let's keep it for the moment on the back of our minds. Now we have to discuss the relation of this calculation to the actual goal of our discussion, namely how is it related to the prepotential. So well, it turns out that adding this observable to the action can be interpreted as changing the Baer coupling constant in a way. So we add to tau naught something which is superspace dependent. So this is a superspace dependent coupling constant. It quadratically depends on both the bosonic and the fermionic coordinates on the chiral part of the superspace. And now, if we remember the relation between this Baer coupling constant and the infrared effective scale lambda, which enters the prepotential of the effective theory, then we would conclude that while we have an effective theory where now the scale lambda varies over the superspace. So if we just substitute this fact into the definition of the prepotential, we can expand it in the superspace, and we'll get a polynomial in odd variables as usual. And then we would like to integrate this expanded prepotential over the superspace to produce the effective action in the components. And that we can use to evaluate the expectation value of our observable using the low energy effective action. So actually, the only term which will contribute to this expectation value will be this last term, so the term with the maximal number of fermions. That is because the terms with smaller number of fermions will necessarily contain gauge fields. And if I do the calculation in the very, very far infrared, the contribution of these gauge fields will be suppressed. And so I can take my space-time metric to be very large, and I will suppress it by an arbitrary value. And because of the supersymmetry of my observable, this value should not matter, and so actually should cancel anyway. So this argument shows that this expectation value we are interested in is given by the simple, so it's an exponential of the integral over R4 of the second derivative of the prepotential with respect to the log of the scale, up to the terms which are proportional to the derivatives of h. So these terms appear because of the failure of this adiabatic approximation. So this argument was correct, of course, if h was a constant, but if h is not a constant, we should only trust this argument up to derivatives, as the low energy effective action is the expansion in derivatives. So we should expect, the terms which will vanish as epsilon go to 0. And now this integral can be easily evaluated because you can essentially change variables and get an integral over h. So you have h dh, and this is essentially d over dh squared. So it's a simple integral. And the answer is very simple. It says that this z, this expectation value, should be given by the exponential of the instanton part of the prepotential. So it's a part which does not contain logarithms over epsilon 1, epsilon 2, plus something which is regular as epsilon goes to 0. And so now we can equate the left and the right hand side. So this is the prediction from the infrared analysis, and this is the ultraviolet calculation, if you wish, the calculation using the instantons. And so the prediction is that there exists a function which is analytic in epsilons, such that when you exponentiate it, divide by epsilon 1, epsilon 2, you can expand it as a sum of various n tuples of Young tableaus, and the contribution of each Young tableau we calculated previously. And then if I take these epsilons to 0 in this function, then I should recover the instanton part of the prepotential of the SU n equals to Young-Mills theory. And so, this looks, at first sight, this looks like a very unlikely fact to be true, because, well, here I have some rational functions of epsilons with increasing singularity as instanton charge increases in epsilon as epsilon goes to 0, and somehow they should combine into some exponential with the only singularity of the first order as epsilon 1 as epsilon 2 goes to 0. So to convince ourselves, let's do some experimental checks. So experimental checks mean that we do this calculation and then we compare with what is known from the actual Zyberg and Witten solution, which I didn't describe because of lack of time. So in principle, there is a way of extracting these instanton corrections from some curves, some families of curves. And so there is a way of getting these instanton corrections to the prepotential by a painful but straightforward procedure. So in principle, we should know the left-hand side here. And so, well, it's not a hard thing to do the first, let's say, first 3 instantons. The formulas are not so horrible. All this is done just by hand. I mean, it's a hand calculation. And indeed, so you get these formulas, and the first 2 agree with what people were obtaining by direct evaluation of the instanton integrals, and this one was not available in the literature. So, but if you compare it to curves, then you get a perfect agreement. And actually, you can go up to 5 instantons without much troubles with the measure. And so I don't have much time. I'll just write down the generalization of these integrals for the various matter contents. So you can consider gauge theory where you add matter hypermultiplets in various representations. And so this is what you get for adjoint representation. This is what you get for fundamental representation. Fundamental is the simplest case. You just have these polynomials in the numerator. And as I published the paper, I got an email from Howard Schnitzer asking about other representations, and so I included this. So if you take a fundamental and a symmetric tensor representation, then this is what you get. And if you want to anti-symmetric tensor representation, then you just relax these to the strict inequality. And again, these formulas agree with the available results in the literature. So how much time do I? This is amber. 0. Okay, sorry. Then I stop here. If there are no questions, I can just flash the rest of the transparencies. Okay.
Are there any other questions?